This is a chem study film produced by the Chemical Education Material Study for use in its course in chemistry. One of the most beautiful sights of nature is the rainbow. This lovely spectrum is familiar to us all. But it was only some 3 centuries ago that man first succeeded in producing his own spectrum, and not until the present century that we began to use it in chemistry as a tool in the study of molecules. Isaac Newton first used a prism to break up sunlight, and thus demonstrated that such white light could be separated into different colors which might be regarded as its components. At the start of the last century, Herschel set up a spectrum just as Newton had done, except that instead of merely using his eye to examine the colors, he used a detector. To his surprise, the detector showed the presence of radiation even beyond the red end of the visible spectrum. Now today we have more delicate detectors than Herschel had. We can easily show the presence of infrared radiation using an ordinary exposure meter. I've covered the light-sensitive element, leaving only a small slit. Here, the meter reads about 1 because of scattered room light. In the middle of the visible spectrum, it reads about 6.5. Here, beyond the visible, in the infrared, it reads about 4. We see that beyond the red light waves, there are infrared waves with a still longer wavelength and a still lower frequency. Here, we have a spectrometer which scans the infrared spectrum and draws a graph of the transmission of the sample in the infrared. In this spectrometer, the instrument runs through frequencies in the infrared range, around 10 to the 13th cycles per second. The top of the chart corresponds to 100% transmission, the bottom to 0 transmission. For our first infrared sample, let's try a simple molecule, HCl in the gas phase. We start recording and scan to lower frequencies. The HCl sample is transparent at all frequencies until we get to 8.67 times 10 to the 13th cycles per second, where the sample absorbs quite strongly. The quanta absorbed have an energy of about 9 kilocalories per mole. At lower frequencies, the HCl is again transparent. Now we must ask ourselves why a nice, simple diatomic molecule like HCl would have such a spectrum as this. According to our model, light involves wave motion. Let's investigate the way in which waves of another sort interact with matter. If we suspend the sphere from a spring, then it will have a natural frequency of vibration of its own. If the waves passing by the sphere push it up and down with this same natural frequency, there's a very strong interaction, and we get a considerable disturbance of the sphere. If the frequency does not match, then, although the waves push the sphere around, we don't get the same sort of strong interaction. There is little absorption of energy by the sphere in spring from the waves going over it in the water. If the frequency of the light wave is the same as the natural frequency of vibration of the molecule, then there'll be synchronization. The molecule will absorb energy from the light wave, and the molecule will vibrate more and more vigorously. Now, the way in which the light wave lays hands on the molecule has to do with the fact that the light wave is accompanied by an oscillating electrical field, while the molecule has different electrical charges on its different atoms. The left to right electrical field will push the positive atoms a little to the right, negative atoms a little to the left, and the right to left electrical field will do just the reverse. We can reproduce this condition by using an electrical generator to charge two condenser plates. With one charged positively and the other negatively, we can switch the charges back and forth and simulate the oscillating electrical effect of a light wave. To model the hydrogen chloride molecule, we can use two lightweight spheres connected by a spring. These, of course, represent one hydrogen atom and one chlorine atom, held together by a bond. The spring rather accurately represents the bond. We have put a positive charge on the hydrogen and a negative charge on the chlorine. With this motor, we can switch the charge on the condenser plates back and forth, and we can observe the effect of the oscillating electrical field on our model of a molecule. We start with the system at rest and slowly increase the frequency of the oscillating electrical field so that in effect we scan the spectrum of different frequencies. At first, there is no interaction between the field and the two charged spheres, but when we reach a certain frequency, which corresponds with the characteristic frequency of our mechanical model, we see that the model begins to vibrate. But if we increase the frequency still more so that we exceed the characteristic frequency of the system, we find that again there is no interaction. The energy of the wave is not absorbed. Now we've seen how a diatomic molecule produces its typical infrared vibrational spectrum. Let's go on and consider what happens in the case of polyatomic molecules. We can learn something about their vibrations by the use of a model of the carbon dioxide molecule. The center sphere represents the carbon atom, and the oxygen atoms are on each side. We activate the model by using a motor-driven eccentric, which is coupled to the molecule by a very loose spring. Of course, if this were a real molecule, it would be pushed on by the oscillating electrical field of the light wave, just as we saw in the case of the HCl molecule. As we attempt to excite vibration very slowly at first, you can see how the molecule flops around rather loosely, but doesn't really fall into any organized, repeating pattern of vibration. When we slowly increase the frequency, we reach a point where the vibration of the molecule falls into a nice characteristic pattern called a normal mode. The molecule has reached one of its natural frequencies of vibration. At this particular frequency, it can vibrate in the normal mode you see here, with the molecule moving its atoms perpendicular to the bonds or springs, with the carbon atom moving up at the same time the oxygen atoms move down. Now, as we turn up the frequency, we once more leave the regular pattern of a normal mode, and the molecule falls into wild, chaotic motion with no regular pattern to it. As we increase speed, we reach another normal frequency where the atoms begin again to execute a smooth, characteristic vibrational pattern. We note that at this frequency, the molecule has its atoms moving along the line of the bonds in a nice symmetrical fashion, with the two oxygen atoms breathing in and out and the carbon atom staying fairly still. By increasing the frequency again, we get away from synchronization, and the molecule again shows only chaotic motion. As we approach the third normal frequency, we see that the molecule is moving in an unsymmetrical fashion, with the carbon moving one way and the two oxygens the other. We would find the same three characteristic types of motion in the actual carbon dioxide molecule. It would move like this at a frequency of 7.05 times 10 to the 13th cycles per second, the highest natural frequency of vibration. Like this at 4.16 times 10 to the 13th cycles per second. And like this, at 2.00 times 10 to the 13th cycles per second, the lowest natural frequency. These three frequencies are all the components we would find in any vibrations of carbon dioxide, and any motions can be analyzed in terms of these three characteristic patterns. This is a carbon tetrachloride spectrum. The dominant feature is due to stretching of the carbon-chlorine bonds. The chloroform spectrum shows absorptions here and here, both of which are associated with motions of the hydrogen atom. A particularly interesting and useful fact is that the molecule retains its characteristic spectrum no matter whether the pure compound or its solutions are studied. If we contaminate a carbon tetrachloride sample with a small amount of chloroform, it's a simple matter to put some of the sample in a small cell and measure its infrared spectrum. The spectrum of the mixture will show not only the characteristic features of the predominant carbon tetrachloride, but also those of chloroform. The intensity of the latter is dependent on the extent of the contamination. These three strong characteristic frequencies of chloroform show up nicely here, here, and here, clearly revealing its presence in the carbon tetrachloride. Now, what about absorption by HCl in other regions of the spectrum? Way back in 1925, Cherney found that HCl gives a characteristic absorption pattern at very low frequencies in the infrared. These regularly spaced absorption frequencies are much too low to be interpreted as vibrations. But a great deal of work since 1925 has established that these absorptions are associated with rotational motions of the molecule. We've seen why the vibrational spectrum of a diatomic molecule contains only a limited number of features, for the light must be absorbed in quanta corresponding to the natural vibrational frequency of the molecule. But there is no such natural frequency of rotation easily pictured. We must apply quantum theory to the model of a diatomic molecule in order to understand the arrangement of rotational energy levels. We can picture them as a staircase. The height of the first step is different for every diatomic molecule, depending on the masses and the bond lengths of the particular molecule. The height of the second step is always twice the height of the first step. The height of the third step is 3 times that of the first, and so on, increasing regularly as we go up. The molecules in higher energy levels rotate faster than those in lower levels. We can explain the regularly spaced rotational spectrum if we use the simple rule that the molecule can jump only 1 step at a time. For HCl, the first step has a height of about 60 calories per mole, 60 small calories. It's a very little step indeed, and when the molecule makes the jump, we get absorption at 60 times 10 to the 10th cycles per second, a very low frequency, 1,000 times slower than that of the vibrational spectrum. The next step is 120 calories per mole. This time we get absorption at 120 times 10 to the 10th cycles per second, and so on up the staircase. The importance of the rotational spectrum to the chemist lies in the fact that it's possible to calculate the length of the hydrogen-chlorine bond from the frequencies of the absorption lines. From this particular spectrum, the length of the HCl bond is calculated to be 1.275 times 10 to the minus 8th centimeters. Although we've talked mainly about very simple molecules, the spectra of more complex molecules can be interpreted in a similar way and yields valuable information about the length, and the springiness of chemical bonds. We cannot see the actual molecules with the naked eye or even with a microscope, but through spectroscopy, we can get detailed information about the position of the atoms in the molecule and the forces that hold them together. Molecular spectroscopy is the key to an understanding of molecular structure, and a knowledge of molecular structure is the key to modern chemistry.